Next example is the calculation of the electric field from a charge uniformly distributed on a straight line, an infinitely long straight line. Okay, if we have charge uniformly distributed on a straight line which is infinitely long, like this. Okay, and first assume that the charge is positive. We can do the same calculation for the negative charge, but just reverse the direction of the electric field. Okay. Now, if we want to calculate the electric field at this point, for example, what is the electric field at this point? Okay. Again, if we want to use the Gauss law in this problem, we need to consider, or we need to look, or we need to find the symmetry of the problem. And in this case, we can see that the problem has cylindrical symmetry. Cylindrical symmetry. It means that if we look on a circle, or more precise, on a cylindrical surface, okay, which has the line charge on its axis. It means that the line charge, this line charge is the axis of this circle. First, okay, let me generalize this to the cylindrical surface, okay, which has the point that we want to calculate the electric field on the surface. Okay. If the distance from the line charge to the point of interest is R, so the radius of this cylinder is R. Okay, and if the height of this cylinder is H, we construct this cylindrical Gaussian surface. Cylindrical Gaussian surface that have our point of interest on the surface, because we can see that the problem has the cylindrical symmetry. The cylindrical symmetry here means that first, the magnitude of E is constant cylindrical Gaussian surface. Okay. E is constant on the cylindrical Gaussian surface. It is because we use the same reason as in the previous example, that if we look at any point on this cylindrical surface, okay, if I look at this point or this point or this point or this point, and when I look back to the line chart, I must see the same picture. It means that the picture when I look at the line chart at these 4 points are identical. So there's no reason that we should have the different value of the magnitude of the electric field on these 4 points or on any point on the cylindrical surface with the same radius r. Okay, it means that you are on this surface, so you see the same picture. So we can expect that E is a constant on the Gaussian surface. Second, we can assume that E, the electric field vector point, or we can, it may be better than, okay, point along the radius direction okay. It means that if we look at the direction of the electric field, we should have that the electric field point outward along, in this case it point outward because the charge is positive, but if the charge is negative, it will point inward. If the charge is negative, it will point inward, but in this case the charge is positive, so it points outward. But inward or outward, it will point in the radial direction. We use the same reason as in the previous example, that is, if the charge, if the electric field does not point in the radial direction, so it means that if we look at the electric field in this direction and in the opposite direction, we will see the different thing. But that should not be the case, because when we look at the line chart in this direction and in this direction, we will see the same picture. Okay. One important thing is that in this problem, the chart is infinitely long. We cannot expect this. We cannot have these two expectations if the line chart has finite length, because the symmetry is destroyed. But if the chart is infinitely long, when you look at something very large, and if you not are at the limb, when you look around, you will see the same picture. Okay, so it means that the best condition or the best choice of the direction of E is that it points outward in the radial direction. So everyone, when look at this electric field vector will see the same thing. I mean everyone on the surface, okay, on the surface of the cylindrical Gaussian surface, you see the same thing. If you look and the direction of your side has some symmetry. Okay, so we have these two assumptions, or we can expect the property of the electric field, these two properties of electric field. Now, we can see that from this one, the electric field will parallel to the vector dA. If you divide the Gaussian surface into small pieces and look at this piece of dA, the vector dA will point outward, mean perpendicular to the surface. So we have that E is parallel to dA on this surface around it. But on the top and the bottom, you can see that if we look at the electric field on the top of the cylindrical surface, E point outward in the radial direction. You can see that on the top and bottom of the Gaussian surface, E is perpendicular to dA, because in this area the dA vector point upward like this, or dA vector point downward like this. So so on the curved part of the Gaussian surface, we have this condition. But on the flat part, which is on the top and at the bottom, we have on the top and the bottom. Okay, it's better to say top and bottom part. Okay, E is perpendicular to dA. So in this part, we must have that E dot dA is equal to 0, while in this part we have that E dot dA is equal to dA. Now, when we have enough symmetry on our problem, you can see that we can use the Gauss law to calculate the electric field at this point. Now, the process is the same, that is, we calculate the total flux on this Gaussian surface that includes the point of interest. Okay, so the total flux is equal to the integral over the closed surface of E dot dA. We can write this integral to be the integral on the curved part. Okay, on the side of E dot dA plus the integral on the top and bottom of E dot dA. Okay, but from this relation we know that this term go to 0, and from this relation we have that this term go to integral of E dA. Okay, and again we use the first expectation that E is a constant on the Gaussian surface, so we can take E outside the integration. So we have this equal to E of integral of dA. But the integral of dA is nothing but the surface area. Okay, so we have that this equal to E 2 pi h. Okay, and now we use the Gauss law that this term is equal to Q over epsilon 0. Okay, we say that the charge is uniformly distributed on the infinitely long line. If we know that the linear charge density, okay, if we know that the linear charge density is equal to lambda, so we must have that this Q is equal to the lambda h over epsilon 0. This Q is equal to lambda h because when we use the Gauss law, we will consider only the charge inside the Gaussian surface, and the charge inside the Gaussian surface is the part of the line charge with the length h, right? With the length h. So the charge in the Gaussian surface is a lambda h, where lambda is the linear charge density. So we have that this term is equal to E is equal to lambda over 2 pi epsilon 0 r. Okay, this is the magnitude of the electric field at the point of our interest, and the direction point outward in the radial direction. Okay, so we finally calculate the electric field at this point. Be careful that this process, we can use this process because we have the symmetry on our problem, and it means that we have the infinitely long charge. If we have the finite charge, we cannot use this process. We have to use the direct integration instead.